Let's move on to question 9. Okay, we have 10 problems, so this is the second last one. This is in the diagram below, the two smaller circles have equal radii. Okay, we can see that these are two small circles, the radii are equal. Each of the three circles are tangent to the other two circles, and so on. I think the whole diagram, it speaks for itself. This is the picture that we've got. Now, if the width of the rectangle is 4, so that is, width is given as 4, determine its length. So the problem is to find the length of this rectangle. Right, I just want to discuss a few things about these tangential circles. And you got lots of tangents here. You got the four boundaries of the rectangle, or the four sides of the rectangle, are tangents to these circles. And let's just analyze what happens here. Um, let's start here, for instance. If I draw the diameter of the circle, to draw the diameter of the circle, starting from the point of contact of this thing. So the diameter will go through the center and keep going on. It has to come to the other edge, because if it goes through the center of the circle, okay, let's just draw the perpendicular on this side as well. At the point of contact, then what you have here is the radius is perpendicular to the tangent. So you'll have a 90 degrees here, you have 90 degrees here. All right, and this is the center of the circle. So what you have here is really two squares, because the side here is 4, and so therefore this side is 4, and both the radii are equal. So they both will be equal to 2, like this. And this is a rectangle. The rectangle. And but these are radii here, so both of them are equal to 2. So that is why you have the rectangle with all the sides equal to 2. You have a square here, like that. Okay. So let's just hold on with that side. And on the other side, what do we have? We have, again, if you join this point of contact here, oh yes, if you take the common tangent here, and there's one tangent at this point, which is the point of contact, and if you draw the common tangent, like that, then you can see that just as in the other case, and if I join these two points of contact, this point of contact, if I come down to this, it's going to be perpendicular to the tangent, and if you carry on, you'll come to this. So what happens here is that this is also the diameter here, and then so this is 2. This is, both these are equal because they're both equal to 4. This is a rectangle, so you got both of these are equal to 2, and so you have a kind of similar situation like that. The only other point is that these 2 points, if you join these 2 points, you see you got a rectangle. If I take this center here and join it to the center here, right, what I'm going to get is something like this. So I'm going to get a rectangle like that. And this will pass through the point of contact here, and you've got a square here, and so on. So this is a picture that you can see that this whole thing gives. You can break this thing up into several rectangles and squares in this fashion, and you got 1, 2, 3, 4. These 4 points, the midpoints here, and these two the points of contact, they're all going all in the same straight line. All right. And the circle here has got its own center. If you take the center of the circle, the diameter is 2. So each of these will be 1 like that. Okay. Now, actually, in this picture, you can see almost what's going to happen. We need to calculate this entire length here. So from here to here, it's 2. I'm sorry, it's 2. Because this is a square. It's a radii. There's another 2 here, but there's a little piece here, which we can't calculate straight away. But there is a 1 here on this side. Because this piece from here to here is the radius. It's exactly the same as that. So this is 1 at this end. So this part is 1. So the only thing you need to do is to calculate this length here. All right. Now, I'm going to go to the next slide where everything is laid out quite clearly. So here is what we have. All right. This is what I had here. This is 2. This radius is 1. And this is the point we couldn't calculate. But if you join these two centers, they will go through the point of contact. That's very important. If you join the centers of two touching circles, right, it'll go through the point where they touch. So those 3 points are in the same straight line. So what happens is, now you have a right angle triangle because this is the radius. It's perpendicular to the common tangent. And this side here is 1. It's the radius of the circle. But the hypotenuse is that one, and it's 3. So you have a right angle triangle where the hypotenuse is 3, and the other side is 1. So this, if you come down to, let's just break up. Sorry, just trying to get this thing neatened up here. So you see what we have here is, you've got a 2 here, you've got a 1 here, and then you've got this part here. But this is exactly the same as BC. But this is a rectangle. See? And so BC is a square root of, the hypotenuse is 3, so it's 3 squared minus 1 squared. So any side of a right angle triangle is the square of the hypotenuse minus the square of the other side, because the sum of the squares here is equal to the square of the hypotenuse. All right, so that gives you the answer to the problem, because the answer is 2 plus 1 is 3, plus the middle one, which is square root of 9 minus 1, which is square root of 8. So that's the answer to that problem. Okay, so these touching circles, there are lots of important results here. I hope you just bear that in mind, namely that if you join the centers of two touching circles, it goes to the point of contact. And we use a lot of other important properties here. The radius is perpendicular to the tangent and so on, okay, to come to these various conclusions. Okay. So you can see right at the bottom, I've got hence the length is equal to the square root of 8. There's not so much of calculation, but there's a lot of discussion around this. We have to justify why all these lines go through these points of contact. Okay. So that actually takes us to the last problem. Question 10. Okay, now we have an algebra problem. So what do you have here? You have 1 plus half, and you're multiplying it by 1 plus 1 over 2 squared, multiplying that. This is not 1 over 2 cubed, it's 1 over 2 to the power of 4. And the next one is 1 over 2 to the power of 8. You're multiplying all these quantities, and you go up to this monster of a number, 2 to the power of, and you got the index is 2 to the power of 2009. I'm going to give a name. That index is very, very cumbersome to work with. So if we let a be equal to 2 to the power of just this index or the exponent, that's 2 to the power of, this is an enormously large number. It's got over 600 digits, right? Now, you've got, that is just the index here. So this last thing is 1 plus 1 over 2 to the power of, that index is a. So you got 2 squared, 2 to the 4th, 2 to the 8th, and the last denominator is 2 to the a, where a is that little thing. Okay, let me go to a new slide because I want to calculate this thing. Okay, so you need to calculate the left side and write it in this form. And the question is, what is this index n here? Okay, so that's looks like a very difficult problem because you got so many factors here. All right, so let's do this slowly. Okay, now remember, I'm going to call a equals 2 to the power of 2009. It looks as if this question was set in 2009. That is how we got that a there. So now if you write this thing, the common denominator is 2. So you get 2 plus 1 over 2. Here the common denominator is 2 squared. And you get 2 squared. I'm not simplifying this. 2 squared plus 1. And here the denominator is 2 to the 4. 2 to the 4th plus 1. I'm not simplifying it because I want to preserve the patterns. When you start working on the numbers destroy the patterns. So here you got 2 to the 8 at the bottom. You got 2 to the 8 plus 1. Right. And then you got all these things multiplied. And here you have 2 to the power of a. Right? This index, we called it a. And just like the others, this will be 2 to the a plus 1. Right? Okay. Now, this is what this is equal to. It's a product of all these. I'm going to put brackets here. I just want to preserve this. So the denominator, you're multiplying everything. So we can write the denominator as 2 times 2 squared times 2 to the 4th times 2 to the 8th. all times 2 to the power of a. And we multiply all those things at the bottom. That's what you get. And you see, everything is being multiplied here. So we're not adding, we're just multiplying. Now, here you got these things are being multiplied. So you got, let me just take the numerator. I'm going to do it here. We'll call it n. N is the numerator. 2 plus 1, 2 squared plus 1, multiplied, 2 to the 4th plus 1, 2 to the 8th plus 1, and so on, going up to the 2 to the a plus 1. I'm going to multiply, I'm just working out the numerator. Now, how do you multiply this? Now, there's a beautiful trick which I'm going to use. Never ever done this before. I'm going to solve this thing here by multiplying it by 1. How's that? I'm going to multiply this by 1. And I say I can multiply this entire thing just by multiplying 1. Now, instead of 1, I'm going to put 2 minus 1. Okay. Because 1 is 2 minus 1. So I'm going to multiply by 2 minus 1. The sum doesn't change. Now watch. If I multiply the first 2 terms, and remember, very important formula, x minus y into x plus y is x squared minus y squared. Right? If you take ones, x minus 1 into x plus 1 is x squared minus 1. X squared minus 1 squared. So that's what I've got here. X minus 1 into x plus 1. So when you multiply these two, you have 2 squared minus 1. Now, that from here to here is 2 squared minus 1, but I'm going to multiply that by 2 squared plus 1. So when you come down to this part here, the 2 squared minus 1 into 2 squared plus 1. So that is 2 to the power of 4 minus 1. 2 squared all squared is 2 to the power of 4 minus 1. Now, this 3 things together multiply together gives you 2 to the 4 minus 1. And now I've got 2 to the 4 plus 1 here. Right? So you got 2 to the 4 minus 1 times 2 to the 4 plus 1 is 2 to the power of 4 squared. 2 to the power of 4 all squared. So that will become 2 to the 8 minus 1. Exactly the same as this. So this becomes 2 to the power of 16 minus 1. Right? If you analyze this, you see what you have here, that this whole thing will be equal to 2 to the power of something minus 1. But what is this something? Now, you'll notice that underneath this, I've got 8, 16, 4, 8, 2, 4. Right? So the power here will be twice the power there. Right? 8 goes to 16. So this will be 2a. Right? In other words, this entire thing simplifies to 2 to the power of 2a minus 1. Because we are multiplying it term by term, and this is the product of this. So what we got here is the product of the whole lot. So your numerator is 2 to the power of 2a minus 1. Oh, you should be so careful here. That's your numerator. Now let's have a look at the denominator. I'll take out all these calculations. I don't need this anymore. Okay, let's have a look at the denominator. Now the denominator is, let's call it D. The denominator is 2. You got the same base, right? And you're multiplying these things. So you can add the indices. So the indices, the first index is 1. It's 1 plus 2, not plus 3, but plus 4. And here you got plus 8. Right? All the way up to plus A. You'll end up with A. That's the last index. Now, the power here is another funny looking thing. Let's call this 2 to the power of m. And I want to calculate m now. M is a sum. What is m? M is 1 plus 2 plus 4 plus 8 all the way up to plus A. Remember, A is this thing here, this monster number, and I'm just calling it A. Now, how do I calculate this now? Now, this is an example of what you call a geometric series, where each term is 2 times the previous one. Right? This is 2 times the previous one. This is 2 times the previous one. This is 2 times the previous one. And the trick, in whenever you have, instead of 2 times, you could have had 5 times the previous one, 5 times the previous one, and so on. You take that constant multiplier, right? And you multiply on both sides by that multiply. If I had 5, I'll multiply this by 5. Now I've got 2 here, so I'm going to multiply this by 2. There are formulae for this, but we're not going to worry about the formula. I'm going to calculate this thing. So I'm going to multiply this entire thing by 2. When I multiply 2 by 1, I get 2. But I'm going to put that 2 underneath the m. Okay, the next thing is 2 times 2. I'm going to put that underneath there. The next thing is 2 times 4. This is 2m, multiplying every term here by 4. So by 2. So this 2 times 4 is 8. So what you see here is exactly the same numbers there. So even here too, you'll have a here. But remember, the last one will also be multiplied by 2. So that'll be 2a. Right? Okay, so everything is being multiplied by 2. Now, to simplify what m is, all I have to do is to subtract these two. 2m minus m is m. I'm going to subtract this way. The bottom one line minus the top line. Right? 2m minus m. Now this 1 becomes minus 1. But then these cancel. 4 minus 4, 4 minus 4, 8 minus 8, a minus a. A lot of these things cancel. The only survivors are this minus 1 and 2a. So this is 2a minus 1. Right? So your m is 2a. But what is m? M was this thing here. So this, I can replace the m here by 2 to the power of 2a minus 1. The m is equal to 2a minus 1. All right. So let me take out all this stuff here now. I've used this and simplified everything quite nicely. I don't need this. Okay, so my denominator, this is your denominator, which are calculated to be this. So let me replace the denominator, this whole denominator here. That's what I call D. And I worked this thing out to be 2 to the power of 2a minus 1. Okay, so I can Uh, I can even take this out now because I've used. Okay, so this thing simplifies to this. Now, I want to come to this part here. I can see somewhere I'm nearly there, but I got a 2 outside. But if you look at this part here, this is equal to 2 to the power of 2a over 2. Right? If 2 to the power of 2a over 2 is, you subtract the indices and you have 2a minus 1. So the denominator, I've got 2a over 2. So if I take that, the 2 at the bottom, and bring it to the top, the thing changes. But now you have 2 to the power of 2a minus 1 over 2 to the 2a. Right? This is 2a, 2 to the 2a over 2. If you the denominator, you push it to the top. And now this is 2 to the power of 2a, 2 to the power of 2a over 2 to the power of 2a is 1, minus 1 over 2 to the power of 2a. Now that looks very much like this. See, these two look very much the same. I've got a 2 here and I've got a 1 minus. The only thing is, I want to just match these two things. So you have 2 to the power of, this denominator is 2 to the power of 2 to the power of n. That denominator 1 over, that will be equal to 2 to the power of 2a. It'll be equal to 2 to the 2a here will be equal to that thing there. Right? Now I go to a. Oh, so what does this mean? They got the same basis, so therefore 2 to the power of n is equal to 2a. 2 to the power of n equals 2a. Now I can finally substitute for a. And so you can see this is a very good move to replace this thing here by a. Otherwise, you'll have to carry this huge, terrible thing all over the place, and I found it very hard to work with it. Okay, now, okay, you got the same base here, so you can add indices. 2 to the power of 1 plus 2009 is 2010. So you got 2 to the n equals 2 to the power of 2010, and that finally tells you that n is equal to 2010. That's the answer. Okay, quite a mouthful, but you'll notice that I kept working this thing out and deleting all the calculations and continuing to get back to what the original problem was, and that's how we were able to ultimately disentangle this rather monstrous problem. Okay, that's the last question. Thank you very much for listening, and we now finished 2023 junior team competition, the 10 questions. And we also have 2024 and 2025. I invite you to have a look at those as well. And you can see there's a really hard problem. These problems here are like final round, third round, even more difficult, the third round Olympiad problems. And some of them are almost like the IMO problems. So they give a very difficult problem. That is why nobody ever gets 100% in the last 20 or 30 years. Okay. So that brings me to the end, and have a good day or good evening.